Part 3 on circuits. The purpose of this lab is to use the principles of energy conservation in order to predict the behavior of various circuits with resistors, to measure the conventional current and potential differences of circuits, and to observe the behavior of resistors and capacitors. A preview is that I equals V over R correctly predicts current. Faster current through a capacitor corresponds to less resistance, and the RC time constant is 0.1667. Some fundamental principles: we have the conservation of energy, which basically states that the sum of all potential energies is zero in the cases of circuits. So basically energy in equals energy out. Conservation of charge says that the total charge stays the same in a loop. Basically that charge cannot be created or destroyed. And then finally we have Ohm's law, which says that voltage equals current times resistance. And you can rearrange this formula to get current equals voltage divided by resistance, which you can see over here. So an overview, this is going to be all in a simulation online. There are three main parts. The first one is to predict the current in a circuit with known voltage and resistance. Then I'm going to graph the voltage over time. Number two, I'm going to experiment with capacitors in different circuits to see how they react to different levels of resistance. And number three, I'm going to allow a charged capacitor to illuminate a light bulb, record the voltage over time, and then use that plot to find the RC time constant. The system and surroundings are listed here, as well as the initial conditions. So for part one, I made a circuit. You can see there are two batteries and two resistors, and then here are, they measure the current. Using this formula, Ohm's law, I got the predicted current of 0.0204 amps, and the measured current by this reader was 0.02, so obviously very similar, and the prediction was pretty good. Continued, we can just double check that the voltage is 3, and you basically just add up the 1.5 volts from each battery here. And then here's a graph of the voltage throughout the circuit. So this is the voltage going up from the batteries, and then it kind of stays the same until it hits the first resistor, and then this is hitting the second resistor, and then it goes back to 0. Part 2, we have resistor capacitor units, circuits. And so when I ran this circuit, the capacitor gained charge, and as it did that, the light bulbs lost charge. And then once this capacitor was fully charged, it was able to charge the light bulb for a short period, and then it lost its charge. Part 2 continued, just playing around with some of the circuits. I found out that the capacitor was slower to charge when it was connected to a higher resistance light bulb, and it was also slower to discharge when connected to a higher resistance light bulb. So we can conclude that a faster charge happens with less resistance. Part 3, so I created a circuit with a 9 volt battery, a 30 ohm light bulb, and a 0.2 F capacitor, as you can see here. And then, yeah, I charged and discharged the capacitor. So when I was discharging the capacitor, I plotted the voltage change with this thing over time, and I got these numbers over here. And then I plotted the natural log of V divided by V naught over time. Then I got this formula right here. And so because we know that this formula right here is equal to negative T divided by RC, we can plot the natural log versus time, and then we know that the slope is going to be equal to negative 1 over RC. So just solving this equation, we get 0.1667 for the computed RC. Now if we're going to use another method, for the expected RC, we use resistance times capacitance, which is 30 times 0.2, and then we get 6. So we can see that these numbers are pretty different. Some sources of error is that it was pretty difficult to get accurate stopwatch times since I was just like recording it on my phone and then copying it by hand into this table, so there was a lot of room for error there. Discussion: what if I was doing this experiment in real life and used an actual ammeter? What would be the difference? The difference is that a real ammeter will have a little bit of resistance because it's not possible to get no resistance, but the online simulator assumes that there's no resistance. So this would have made the circuits in real life have less current. So what if I was doing this in real life and used a real battery to charge a real capacitor with no resistance? How quickly would the capacitor reach full charge? Well, you'd expect it, the ideal model would predict it to reach full charge immediately because there'd be no resistance, but in real life there is some resistance that cannot be ignored. So, thank you.